Welcome to the TCP/IP module of the Networking Fundamentals for Industrial Control Systems course. This module introduces the student to the concepts and characteristics of the IP and TCP layers of the TCP/IP network protocol stack and the concepts of IPv6. After you complete this module, you will be able to describe basic WAN concepts, cabling, and protocols, explain the characteristics and functions of the IP network layer, describe IPv4 and the IPv4 addressing scheme, identify the concepts and characteristics of IPv6, and describe the concepts, functions, and protocols used to process data at the TCP/IP transport layer. In this lesson, you will be introduced to wide area networking technologies, WAN devices and cabling, as well as Layer 2 WAN protocols and the major WAN communication link options. A wide area network is a data communications network that operates beyond the geographic scope of a LAN. WANs use facilities that are provided by a service provider or carrier, such as a telephone or cable company. WANs connect the locations of an organization to each other, to locations of other organizations, to external services, and to remote users. WANs carry various traffic types such as voice, data, and video. There are three major characteristics of WANs to include: WANs generally connect devices that are separated by a broader geographical area than a LAN can serve. WANs use the services of carriers such as telecoms, cable companies, satellite systems, and network providers. And WANs use serial connections of various types to provide access to bandwidth over large geographic areas. There are several reasons why WANs are necessary in a communications environment. LAN technologies provide speed and cost efficiency for the transmission of data in organizations in relatively small geographic areas. However, there are other business needs that require communication among remote users, including the following. People in the regional or branch offices of an organization need to be able to communicate and share data. Organizations often want to share information with other organizations across large distances, and employees who travel on company business frequently need to access information that resides on the corporate networks. Because connecting computers is not feasible across a country or around the world in the same way that computers are connected in a LAN environment with cables, different technologies have evolved to support this need. Increasingly, the Internet is being used as an inexpensive alternative to an enterprise WAN for some applications. There are several devices that operate at the physical layer in a WAN. WANs use numerous types of devices that are specific to WAN environments, including the following: CSU, DSU, digital lines such as T1 or T3 carrier lines requires a CSU and a DSU to prepare the signal for transmission. The two are often combined into a single piece of equipment that is called the CSU/DSU. Typically, this is embedded into the router. Modem. A modem modulates an analog carrier signal to encode digital information and also demodulates the carrier signal to decode the transmitted information. WAN switch. A WAN switch is a multi-port internet working device that is used in carrier networks. This switch may be a Layer 1, Layer 2, or Layer 3 switch. Router. A router provides internet working and WAN access interface ports that are used to connect to the service provider network. These interfaces may be serial connections or other WAN interfaces. Core router. A core router resides within the middle or backbone of the WAN rather than at the periphery. To fulfill this role, a router must be able to support multiple telecommunication interfaces of the highest speed in use in the WAN core. A core router must also be able to forward IP packets at wire speed on all of these interfaces. The router must support the routing protocols that are being used in the core. Devices on the subscriber premises are referred to as customer premise equipment or CPE. The subscriber owns the CPE or leases the CPE from the service provider. A copper or fiber cable connects the CPE to the equipment of the service provider. This cabling is often called the local loop or last mile. The following are three of the numerous wired WAN connection types. Those are CSU/DSU. The router connects to the channel service unit or data service unit with a serial cable, for example, V.35. The CSU/DSU then connects to the service provider infrastructure using a telephone or coaxial cable, for example a T1 or E1 line. Devices that put data on the local loop are called data communication equipment, or CSU/DSU in this example. The customer devices that pass the data to the DCE are called data termination equipment, or in this example, the router. DSL modem. A router connects to a DSL modem using an Ethernet cable. The modem connects to the service provider network using a telephone cable. Optical fiber converter. An optical fiber converter is where a fiber optic link terminates and where optical signals are converted into electrical signals. The converter can also be implemented as a router or switch module. In addition to physical layer devices, WANs require data link layer protocols to establish the link across the communication line from the sending to the receiving device. On each WAN connection, data is encapsulated into frames before crossing the WAN link. To ensure the correct protocol is used, you must configure the appropriate Layer 2 encapsulation type. The choice of Layer 2 protocol depends on the WAN technology and the communicating equipment. PPP, HDLC, frame relay, MPLS, ATM, Ethernet, and broadband are typical WAN protocols. Point-to-point protocol provides router-to-router and how-to network connections over synchronous and asynchronous circuits. PPP was designed to work with several network layer protocols, including IP. PPP also has built-in security mechanisms such as PAP and CHAP. High-level data link control is the Cisco default encapsulation type on point-to-point connections, dedicated links, and circuit-switched connections. HDLC is a bit-oriented, synchronous data link layer protocol. Frame relay protocol is an industry-standard switched data link layer protocol. Frame relay defines how connections between DTE and DCE are maintained for remote terminal access and computer communications in public data networks. Multi-protocol label switching protocol provides an intermediate encapsulation between the Layer 3 IP header and any Layer 2 header. This additional header allows forwarding packets through a network without the inspection of the IP layer header at each forwarding node. Initially developed to increase the speed of route forwarding process, MPLS is widely used today in service provider network cores and large enterprises due to the ability to accommodate multiple services such as Layer 3 VPN offerings, traffic engineering, and tunneling of Layer 2 services such as ATM and frame relay. For most enterprise applications, the enterprise site connects to the service provider using a Layer 2 protocol such as PPP or Ethernet. The service provider inserts the MPLS encapsulation on the packet at the edge of the service provider network. ATM is the international standard for cell relay in which multiple service types, such as voice, video, and data, are conveyed in fixed-length 53-byte cells. ATM, a cell switch technology, uses fixed-length cells that allow processing to occur in hardware, reducing transit delays. ATM is designed to take advantage of high-speed transmission media such as T3, E3, and Sonnet. The emergence of Ethernet as a viable method of providing both point-to-point and multi-point services has been driven by an abundance of new fiber deployment to the business area. Ethernet may be the most scalable transport technology ever developed, starting at 10 megabits per second, evolving now to 100 gigabytes per second. Broadband in data communications refers to data transmission in which multiple pieces of data are sent simultaneously to increase the effective rate of transmission, regardless of the actual data rate. In network engineering, this term refers to transmission methods in which two or more signals share a medium, such as the following technologies: DSL, PPoE, and PPoA. These are a family of technologies that provide digital data transmission over the wires of a local telephone network. Cable Ethernet. A cable modem is a type of modem that provides access to a data signal that is sent over the cable TV infrastructure. There are a number of ways in which WANs are accessed depending on the data transmission requirements for the WAN. Many options for implementing WAN solutions are currently available. The options differ in technology, speed, and cost. WAN connections can be either over a private infrastructure or over a public infrastructure such as the Internet. Private WAN connections include dedicated and switched communication link options. Dedicated communication links. When permanent dedicated connections are required, point-to-point lines are used. A point-to-point link provides a pre-established WAN communications path from the customer premises through the provider network to a remote destination. Point-to-point lines are usually leased from a carrier and are also called leased lines. Switched communication links. Switched communication links can be either circuit switched or packet switched. Circuit switching dynamically establishes a dedicated virtual connection for voice or data between a sender and a receiver. Before communication can start, establishing the connection through the network of the service provider is necessary. Examples of circuit-switched communication links are analog dial-up, public switched telephone network lines, and integrated services digital network. Packet-switched communication links. Because the data flow in many networks fluctuates, communication providers have transport networks that are available to more appropriately service these users. In packet-switched networks, the data is transmitted into label frames, cells, or packets. Packet-switched communication links include frame relay, ATM, MPLS, and Metro Ethernet. Public connections use the global Internet infrastructure. Until recently, the Internet was not a viable networking option for many businesses because of the significant security risk and lack of adequate performance guarantees in the end-to-end Internet connection. With the development of virtual private network technology, however, the Internet is now an inexpensive and secure option for connecting to teleworkers and remote offices where performance guarantees are not critical. Internet WAN connection links are through broadband services such as DSL, cable modem, and broadband wireless, and they are combined with VPN technology to provide privacy across the Internet. Broadband connection options are typically used to connect telecommuting employees to a corporate site over the Internet. ISPs use several different WAN technologies to connect their subscribers. The connection type that is used on the local loop or last mile may not be the same as the WAN connection type that is employed within the ISP network or between various ISPs. Long-range communications are usually those connections between ISPs or between branch offices in very large companies. In this lesson, you will be introduced to IPv4 addressing and masking, subnets, and the role of default gateways, DHCP, and NAT in data communications. As a component of the TCP/IP stack, IP uses packets to carry information through the network. A packet is a self-contained, independent entity that contains data and sufficient information to be routed from the source to the destination without reliance on earlier exchanges. IP protocol has these characteristics. IP operates at layer 3 of the OSI model, the network layer, and at the internet layer of the TCP/IP stack. IP is a connectionless protocol in which a one-way datagram is sent to the destination without advance notification to the destination device. The destination device receives the data and does not return any status information to the sending device. Each packet is treated independently, which means that each packet can travel a different way to the destination. IP uses hierarchical addressing in which the network ID is the equivalent of a street and the host ID is the equivalent of a house or office building on that street. IP provides service on a best effort basis and does not guarantee packet delivery. A packet can be misdirected, duplicated, or lost on the way to the packet destination. IP does not provide any special features that recover corrupted packets. These services are instead provided by the end systems of the network. IP operates independently of the medium that is carrying the data, and there are two current versions of IP, IP version 4 and IP version 6. The IPv4 header has several fields. These are the two fields that are most important for you at this point. The source address field specifies the 32-bit binary value that represents the IP address of the sending endpoint. The destination address field specifies the 32-bit binary value that represents the IP address of the receiving endpoint. Other fields in the header are the following. The version field describes the version of Internet Protocol. The IHL field stands for Internet Header Length and describes the length of the header. The service type field provides information of desired quality of service. The total length field describes the length of a packet, including header and data. The identification field is used for unique fragment identification. The flag field sets various control flags regarding fragmentation. The fragment offset field indicates where specific fragments belong. The time to live field limits the lifetime of a packet. The protocol field indicates the protocol used in the data portion of an IP packet. The header checksum field is used for header error detection. The options field include optional parameters. And the padding field is used to ensure that the header ends on a 32-bit boundary. Just as physical street addresses are necessary to identify the locations of specific homes and businesses so that mail can reach them efficiently, logical IP addresses are used to identify the location of specific devices on an IP network so that data can reach those network locations. Every host, computer, networking device, or peripheral device connected to the Internet has a unique 32-bit IP address for identification. Without a structure for allocating all of those IP addresses, routing packets efficiently would be impossible. Learning how IP addresses are structured and how they function in the operation of a network provides an understanding of how IP packets are forwarded over networks using TCP/IP. An IP address is hierarchical and consists of two parts. The network address portion, network ID, describes the network of which this IP address is a part. The host address component, or the host ID, identifies a specific endpoint. These endpoints are the servers, computers, and other devices that are connected to the network. Host IDs are assigned to individual devices, such as end-user devices, printers, network devices, and so on. To accommodate networks of various sizes and to aid in classifying them, IP addresses are divided into categories that are called classes. Assigning IP addresses to classes is known as classful addressing. The classes were determined during the early days of the Internet by the Internet Assigned Numbers Authority. As we have seen, each IP address is broken down into a network ID and a host ID. In addition, a bit or bit sequence at the start of each address determines the class of the address and also defines the range of values for that octet that are possible for each type of address. Here are 3 of the 5 IP classes. Class A. This address block is designed to support extremely large networks with more than 16 million host addresses. The Class A address uses only the first octet, or 8 bits, of the 32-bit number to indicate the network address. The remaining 3 octets of the 32-bit number are used for host addresses. Any address that starts with a value between 1 and 126 in the first octet of the 32-bit number is a Class A address. Notice that Class A addresses all begin with a binary 0. Therefore, the value of the first octet can only be in a range between 1 and 127, and value 127 is reserved. Class B. This address space is designed to support the needs of moderate to large networks with more than 65,000 hosts. The Class B address uses 2 of the 4 octets, or 16 bits, to indicate the network address. The remaining 2 octets specify host addresses. Any address that starts with a value in the range of 128 to 191 in the first octet is a Class B address. Class C. This address space is the most commonly available address class. This address space is intended to provide addresses for small networks with a maximum of 254 hosts. If an address contains a number in the range of 192 to 223 in the first octet, the address is a Class C address. Certain IP addresses are reserved and cannot be assigned to individual devices on a network. These reserved addresses include a network address, which is used to identify the network itself, and a broadcast address, which is used for broadcasting packets to all of the devices on a network. The network address is a standard way to refer to a network. An IP address that has binary zeros in all of the host bit positions is reserved for the network address. For example, the IP address 172.16.0.0 is a Class B network address. In the IP address 172.16.0.0, the first 2 octets are reserved for the network address and are never used as an address for any device that is attached to that address. A router uses the network IP address when the router searches the IP routing table for the destination network location. The broadcast IP address of a network is a special address for each network that allows communication to all of the hosts in that network. The directed broadcast address is used when a host knows the network ID of the network and needs information from other stations on the network. If an IP device wants to communicate with all of the devices on the local network but does not know the network ID for the local network, the device sets the destination address to all ones, or 255.255.255.255, and transmits the packet. The local broadcast is never routed. A local loopback address is used to let a system send a message to the loopback address for testing. The loopback address creates a shortcut method for TCP/IP applications and services that run on the same device to communicate with each other. A typical local loopback IP address is 127.0.0.1. Address 0.0.0.0 indicates the host in this network and is used only as a source address. An example use case is the DHCP assignment process before the host has a valid IP address. In addition to the reserved addresses, IP addressing has special ranges of addresses scoped for use in the network, which includes private address ranges for use inside of private networks, like your network at home. These include the 10.0.0.0 address range, the 172.16.0.0 to 172.31.0.0 address range, and the 192.168.0.0 address range. Special purpose addresses include the 169.254.0.0 address range, which is used as a self-assigned address. Multicast addresses for use to distribute multicast data such as IPTV and routing updates across an IP network are in the range from 224.0.0.0 to 239.255.255.255. Experimental addresses for use by the IETF and partner companies when developing new protocols for the IP environment in the range of 240.0.0.0 and up. Network administrators often need to divide networks, especially large networks, into subnetworks or subnets to provide scalability. Here we see the purposes and functions of subnets and their addressing schemes. A company that occupies a 3-story building might have a network that is divided by floors, with each floor divided into offices. Think of the building as the network, the floors as the 3 subnets, and the offices as the individual host addresses. A subnet segments the host within the network. Without subnets, the network has a flat topology. A flat topology has a short routing table and relies on MAC addresses to deliver packets. MAC addresses have no hierarchical structure. As the network grows, the use of the network bandwidth becomes less efficient. There are other disadvantages to a flat network. All devices share the same bandwidth and broadcast domain, and make applying security policies difficult because there are no boundaries between devices. On a switch-connected network, the host sees all of the broadcasts in the broadcast domain. When traffic is heavy, collisions caused by 2 or more devices that are transmitting simultaneously may be frequent. The devices detect the collisions, stop transmitting, and then begin transmitting later at random intervals. To users, this process is perceived as the network slowing down. The switches are improving network performance, but routers are a better choice in these situations. Routers can be used to separate networks by breaking the network into multiple subnets. The advantages of subnetting a network are as follows. Smaller networks are easier to manage and map to geographical or functional requirements. Overall network traffic is reduced, which can improve performance. And you can more easily apply network security measures at the interconnections between subnets than within a large single network. In multiple network environments, each subnetwork may be connected to the Internet by a single router. The details of the internal network environment and how the network is divided into multiple subnetworks are insequential to other IP networks. The use of segmentation is important for the routing operation to be efficient. Let us take a look at the role of the subnet mask within the network. In IP addressing, the subnet mask is configured on the network along with the IPv4 address to define the network portion of the address. That host, along with the IPv4 address, is the portion of the address necessary to perform routing. The subnet mask identifies which bits within the IP address are the network and subnet bits versus the host address bits. If the network has been divided into subnetworks, a portion of the host address field is used to represent the subnetwork address. The subnet address field always follows immediately after the network number and consists of bits that are borrowed from the host portion of the IP address. The subnet mask consists of 32 bits, just as the address does, and although subnet masks use the same format as IP addresses, subnet masks are not IP addresses themselves. How do you know how many bits represent the network portion of the address, and how many bits represent the network, subnet, and host portion? The subnet mask is created by placing a binary 1 in each bit position that represents the network and subnetwork portion of the IP address, and placing a binary 0 in each bit position that represents the host portion. Just as IP addresses are written with dotted decimal values to represent the binary values in the address, subnet masks are likewise seen in dotted decimal values. If the subnet mask is represented by the value 255 in decimal for an octet, then all of the equivalent bits in that octet of the address are network bits. Likewise, if the subnet mask for an octet is represented by the value 0 in decimal, then all the equivalent bits in that octet of the address are host bits. The last column in the illustration shows the decimal representation of the subnet mask for each combination of borrowed bits, representing subnet addresses. One of the decisions you must make when creating subnets is to determine the optimal number of subnets and hosts. This topic describes a process for planning subnets. Consider a Class B network address in which 16 bits are used for the network ID and 16 bits are used for the host ID. Therefore, there are 65,536 possible addresses that are available to assign to host. Of these, 65,534 are usable addresses after subtracting the two addresses that cannot be used, the broadcast and subnet addresses. Now imagine that this Class B network is divided into subnets. If 2 bits are borrowed from the default 16-bit host field, the size of the host field decreases to 14 bits. All possible combinations of zeros and ones that could occur in the remaining 14 bits produce a total of possible hosts that could be assigned in each subnet. Thus, the number of hosts that are assigned to each subnet is now 16,382. In the same Class B network, if 3 bits are borrowed, the size of the host field decreases to 13 bits, and the total number of assignable hosts for each subnet decreases to 8,192. The number of usable host numbers decreases to 8,190, which is 8,192 minus 2. This last example shows 8 subtract 2, or usable subnets in a Class B network. Each of these 6 subnets can have 8,192 minus 2 usable host addresses. Here we see a network that uses fixed length prefixes to address various segments. The subnet address 172.16.5.0/24 used for the portion of the enterprise network attached to router A is generated from subnetting the 172.16.0.0/16 to networks into multiple /24 subnets. Address space is wasted because large subnets are used for addressing point-to-point segments. Each point-to-point segment between the router is assigned to a Class C network, with 256 addresses when only 2 devices are present on that segment. Therefore, only 2 bits of the address space are needed in the host portion of an IP address to create the appropriate subnet. VLSM affords the options of including more than one subnet mask within a network and of subnetting an already subnetted network address. Without the use of VLSM, companies must implement a single subnet mask within an entire Class A, B, or C network number. VLSM allows more hierarchical levels within an addressing plan, which enables easier aggregation of network addresses. In the illustration shown, network 172.16.0.0/16 has been previously divided into subnetworks using /24 masking, which as you can see is still being used at the headquarters router. One of the subnetworks in this range, 172.16.5.0/24, is further divided into smaller subnetworks using /27 masking at routers A, B, and C. These smaller subnetworks range from 172.16.5.0/27 to 172.16.5.224/27 and addresses 172.16.5.32/27, 172.16.5.64/27, and 172.16.96/27 are being assigned to each respective router for the LAN portion of the network. However, as mentioned previously, for each WAN link, you only need 2 IP addresses, one for each end of the connection. In the figure shown, the subnet addresses that are used on the WAN links are generated from subdividing the 172.16.5.0/27 subnet into multiple /30 subnets. Therefore, a subnet mask /30 is used for each WAN subnet, which creates subnets with only 2 host addresses to be used on the WAN links. The /30 subnet addresses here range from 172.16.5.0/30 to 172.16.5.28/30, and the WAN links have been assigned addresses 172.16.5.0/30, 172.16.5.4/30, and 172.16.5.8/30, respectively. This mechanism provides a much more efficient use of the addressing space for point-to-point links in the WAN. In the previous figure, the 172.16.5.0/27 network was further subdivided to provide /30 subnets for the point-to-point segments between the routers. For each WAN link, you need only 2 IP addresses, one for each end of the connection. Therefore, only 2 bits are needed in the host portion of an IP address to create the appropriate subnet. By further subdividing the 172.16.5.0/27 subnet into multiple /30 subnets, we provide 8 times 2 to the third power subnets in 2. In a network environment, the source host is able to communicate directly with the destination host only if the 2 hosts are on the same network. In other words, the hosts share the same network ID, subnet ID, and subnet mask. If the 2 hosts are on different networks, the data must be routed. Therefore, the sending host must send the data to the network gateway. Generally, this is the router, which will then forward the data to the destination. This action is the function of a default gateway. Before an end system can send a packet to the end system destination, the end system must first determine if the destination address is in the local network. The subnet mask defines the network part of the IP address. The end system compares the network portion of the local network address with the destination network address of the packet to be sent. If the network portion of the local network address is the same as the destination network address, then the end system can deliver packets directly. If the network portion of the local network address is not the same as the destination network address, then the packets must be forwarded to some other network. The default gateway is needed to send a packet out of the local network. If the network portion of the destination address of the packet is different from the network of the originating host, the packet has to be routed outside of the original network. To do this, the packet is sent to the default gateway. This default gateway is a router interface that is connected to the local network. The default gateway interface has a network layer address that matches the network address of the host. The hosts are configured to recognize that address as the default gateway. On a Windows computer, the Internet Protocol, or TCP/IP, properties tools are used to enter the default gateway IP address. The host's IP address, as well as the default gateway address, must have the same network portion of the respective default gateway addresses. Originally, network administrators had to manually configure IP addresses and other network parameters on equipment connecting to the Internet or in the respective corporate network. Dynamic Host Configuration Protocol was introduced to automate assignment of network parameters including IP addresses, mask, default gateway information, and so on. Managing a network can be time-consuming. Network clients break or are moved around, and new clients appear that need network connectivity, all part of the network administrator's job. Manually configuring IP parameters and addresses for all devices in the network is impossible in some cases. DHCP can greatly lighten the workload of the network administrator. DHCP is built on a client-server model. DHCP server hosts allocate network addresses and deliver configuration parameters to dynamically configured hosts. The term client refers to a host that is requesting initialization parameters from a DHCP server. DHCP supports three mechanisms for IP address allocation. With manual allocation, a client is assigned an IP address by the network administrator, and DHCP is used simply to convey the assigned address to the client. With automatic allocation, DHCP assigns a permanent IP address to a client. With dynamic allocation, DHCP assigns an IP address to a client for a limited time or until the client explicitly relinquishes the address. In a DHCP environment, an endpoint configured for DHCP will send out a broadcast on the local network looking for a DHCP server. The DHCP server will send a DHCP offer to the client with the assigned address. However, DHCP is much more than just an IP address allocation mechanism. A DHCP server can push other initial configuration parameters to the client devices, such as the time or a log server address. A single server can service multiple networks or broadcast domains by having a scope of addresses defined for each network. A DHCP relay agent is a Layer 3 device that enables the use of a centralized DHCP server by forwarding DHCP packets off of the local network. The relay agent is used when the client and server are in different Layer 3 subnets. Small networks are commonly implemented using private IP addressing as defined in RFC 1918. Private addressing gives enterprises considerable flexibility in network design. This addressing enables operationally and administratively convenient addressing schemes as well as easier growth. Private addresses enable internal data delivery within a private network or between private networks within a single administrative boundary. However, private addresses do not enable data delivery between private networks with overlapping address assignments or to public networks like the Internet. If using private addresses in a network, these addresses cannot be routed over a public network like the Internet, and there are not enough public addresses to allow all organizations to provide a public address to all of their hosts. Therefore, network administrators need a mechanism to translate private addresses to public addresses and back at the edge of their network. Network Address Translation, or NAT, provides this mechanism. Before NAT, a host with a private address could not access the Internet. Using NAT, companies can provide some or all of their hosts with private addresses and use NAT to provide address translation to allow access to the Internet. However, NAT is not always used for public access. NAT can be used for general address translation when devices have overlapping addresses, as often occurs when companies merge or in situations where device IP addresses cannot easily be changed due to equipment or regulatory limitations. NAT can work in the following ways. Static NAT maps an unregistered IPv4 address to a registered IPv4 address one-to-one. Static NAT is particularly useful when a device must be accessible from outside the network. This type of NAT is used when a privately addressed device must be publicly available. For example, when a company has a server for which the company needs a static IP address. Dynamic NAT. This maps an unregistered IPv4 address to a registered IPv4 address from a group of registered IPv4 addresses. This type of NAT is used, for example, when two companies merge that are using the same private address space. With the use of dynamic NAT readdressing, use of the entire address space is avoided or at least postponed. Port Address Translation, or PAT. This maps multiple unregistered IPv4 addresses to a single registered IPv4 address, many-to-one, by using different ports. PAT is also known as NAT overloading and is a form of dynamic NAT. PAT is the most common use for NAT and is used every day in your place of business or your home. Multiple users of PCs, tablets, and phones are able to access the Internet, even though only one public IP address is available for that LAN. In this lesson, you will be introduced to the IPv6, which was developed due to IPv4 address exhaustion. One of the pressing issues in IP networking since the early 1990s is that the scope of IPv4 addresses as defined in the mid-1970s is limited with respect to the way that networks are implemented today. With the boom in connected devices, the total number of available addresses for use with this protocol, over 4.5 billion in total, is not sufficient for a worldwide public network. In an effort to allocate IPv4 addresses efficiently and thereby conserve public addresses as much as possible, classless interdomain routing, or CIDR, was developed. CIDR allowed the address space to be divided into smaller blocks. Variable Length Subnet Mask, VLSM, allows more efficient use of IP addresses, specifically on small segments, such as point-to-point serial links. VLSM usage was recommended in RFC 1817. CIDR and VLSM support is a prerequisite for ISPs to receive additional allocations. The Dynamic Host Configuration Protocol, or DHCP, is used by a client device to acquire configuration information such as an IP address, a default route, and DNS setup from a server. This capability enables efficient time sharing of a pool of addresses in a network. NAT introduced a model in which a device facing outward to the Internet would have a globally routable IPv4 address, while the internal network would be configured with private addresses. These private addresses could never leave the site and could be identical in many different enterprise networks. In this way, even large enterprises with thousands of systems could hide behind a small number of routable public networks. One of the arguments against deploying IPv6 is that NAT will solve the problems of limited address space in IPv4. The use of NAT merely delays the exhaustion of the IPv4 address space by using global addresses for large internal networks. There are several negative implications of using NAT, some of which are identified in RFC 2775 and RFC 2993 as follows. NAT breaks the end-to-end model of IP. IP was defined so that underlying layers do not process the connection, only the endpoints process the connection. NAT inhibits end-to-end network security. Any translation of parts of a header on the path will break the integrity check. When applications are not NAT friendly, which means that for a specific application, more than just port and address mapping are necessary to forward the packets through the NAT device. NAT has to embed complete knowledge of all the applications to perform correctly. Therefore, the NAT device needs to be upgraded each time a new non-NAT friendly application is deployed, for example, peer-to-peer. When different networks use the same private address space and they have to merge or connect, there is an address space collision. This problem can be resolved by techniques such as renumbering or twice NAT. Twice NAT is the practice of changing both the source and destination address of a packet. However, these techniques are costly and later on increase NAT complications. IPv6 includes a number of features that make IPv6 attractive for building global-scale, highly effective networks. The larger address space, strict aggregation, and auto-configuration provide important capabilities. Streamlined header structures make processing IPv6 packets faster and more efficient for intermediate routers within the network, which is especially true when large numbers of packets are routed in the core of the IPv6 Internet. Features that were not part of the original IPv4 specification, such as security and mobility, are now built into IPv6. IPv6 also includes a rich set of transition tools to allow an easy, non-disruptive transmission over time to IPv6 dominant networks. IPv6 also includes a rich set of transition tools to allow an easy, non-disruptive transition over time to IPv6 dominant networks. Here we see IPv6 addresses and different address types. IPv6 addresses are represented as a series of 8 16-bit hexadecimal fields that are separated by colons. The A, B, C, D, E, and F in hexadecimal fields are case insensitive. There are some ways to shorten the writing of IPv6 addresses, such as the leading zeros in a field are optional, so 010F can be written as 10F, and 0000 can be written as a single zero. Also, successive fields of zeros can be represented as a double colon, but only once in an address. An address parser can identify the number of missing zeros by separating the two parts and filling in zeros until the 128 bits are completed. However, if two double colons are placed in the address, there is no way to identify the size of each block of zeros. Therefore, only one double colon is possible in a valid IPv6 address. The use of the double colon technique makes many addresses very small. For example, FF01:0:0:0:0:0:0:1, which is still a very long string of hexadecimal digits, becomes FF01:1. The unexpected address is written as a double colon because it contains only zeros. IPv6 supports 3 types of addresses. Unicast. Unicast addresses are used in a one-to-one context. A multicast address identifies a group of interfaces. Traffic that is sent to a multicast address is sent to multiple destinations at the same time. An interface may belong to any number of multicast groups. An IPv6 anycast address is assigned to an interface on more than one node. When a packet is sent to an anycast address, it is routed to the nearest interface that has this address. The nearest interface is found according to the measure of distance of the particular routing protocol. All nodes that share the same address should behave the same way so that the service is offered regardless of the node that services the request. Each address type has specific rules regarding its construction and use. IPv6 has no support for broadcast addresses in the way that they are used in IPv4. Instead, specific multicast addresses, such as the all nodes multicast address, are used. There are several basic types of IPv6 unicast addresses: global, reserved, private, link local, loopback, and unspecified. A global unicast address is an IPv6 address from the global unicast prefix. The structure of global unicast addresses enables the aggregation of routing prefixes, which limits the number of routing table entries in the global routing table. Link local addresses are new to the concept of addressing with IP in the network layer. These addresses refer only to a particular physical link. Link local addresses typically begin with FE80. The next digits can be defined manually. If you do not define them manually, the interface MAC address is used based on the EUI64 format. Just as in IPv4, a provision has been made for a special loopback IPv6 address for testing datagrams that are sent to this loopback address to the sending device. However, in IPv6, there is just one address, not a whole block, for this function. The loopback address is 0:0:0:0:0:0:0:0:1, which is normally expressed as :1. IPv4, an IP address of all zeros, has a special meaning referring to the host, and is used when a device does not know the host's own address and is sent by a device that seeks to have the host IP address configured. You can apply address compression to this address. Because the address is all zeros, the address becomes just :. The IETF reserved a portion of the IPv6 address space for various uses, both present and future. The local address within each subnet prefix, the interface identifier set to all zeros, is reserved as the subnet router anycast address. The 128 highest address within each /64 subnet prefix are reserved to be used as anycast addresses. The EUI 64 standard explains how to stretch IEEE 802 MAC addresses from 48 to 64 bits by inserting the 16-bit 0xFFFE in the middle at the 24th bit of the MAC address to create a 64-bit unique interface identifier. In the first byte of the vendor OUI, bit 7 indicates the scope, 0 for global and 1 for local. As most burned-in addresses are globally scoped, bit 7 will usually be 0. The EUI 64 standard also specifies that the value of the 7th bit be inverted. So, for example, MAC address 00-90-17-17-FC-0F becomes 02-90-27-17-FC-0F. The resulting EUI 64 address on network 2001:0DB8:0:1:/64 would be 2001:0DB8:0:029:27FF:"FE17:FC0F. The IPv6 address can be completely specified, or the host identifier, the rightmost 64 bits, can be computed from the EUI 64 of the interface. Having a much larger address space that is available, IPv6 engineers designed a way to enable auto-configuration of the addresses while still keeping the global uniqueness. A router on the local link will send network type information such as the prefix of the local link and the default route to all of the nodes on the local link. A host can auto-configure by appending the host data link layer address in a special 64-bit EUI 64 format to the local link prefix 64 bits. This auto-configuration results in a complete 128-bit IPv6 address that is usable on the local link and is most likely globally unique. To avoid the rare event of address collision, a process is enabled to detect duplicate addresses. Auto-configuration enables plug-and-play, which connects devices to the network without any configuration and without any stateful servers, such as DHCP servers. Auto-configuration is an important feature for enabling deployment of new devices on the Internet, such as cell phones, wireless devices, home appliances and networks, and so on. Auto-configuration can be accomplished in two ways: stateless, via neighbor discovery and router advertisements, as previously described, and stateful, using a DHCP v6 server. The difference between the two is that with the stateful method, a record is kept of which hosts are assigned which addresses. The stateless method does not maintain those records. A router announcement can indicate to host whether or not configuration parameters are available via stateful configuration, or DHCP v6, such as DNS, IP options, and so on. The IPv4 header contains 12 fields. Following these fields is an options field of variable length that the figure shows in yellow and a data portion that is usually the transparent layer segment. The basic IPv4 header has a size of 20 octets. The options field increases the size of the IP header. Of these 12 header fields, 6 are removed in IPv6. These fields are in green in the figure. The main reasons for removing these fields in IPv6 are as follows. The Internet header length field was removed because all IPv6 headers are a fixed 40-byte length, unlike IPv4 in which the header length is variable. Fragmentation is now processed differently and does not need the fields in the basic IP header. In IPv6, routers no longer process fragmentation, which is a change that removes the processing issues that result when routers process IPv4 fragmentation. The related removed fields appear in the fragmentation extension header in IPv6, which is attached only to a packet that is actually fragmented. The header checksum field at the IP layer was removed because most data link layer technologies already perform checksum and error control, and because the relative reliability of the data link layer is very good. However, this removal forces the upper layer optional checksums, such as UDP, to become mandatory. The options field is changed in IPv6 and is now processed by an extension header chain. Most other fields were either unchanged or changed only slightly. The IPv6 header has 40 octets instead of 20 octets as in IPv4. The IPv6 header has fewer fields, and the header is aligned on 64-bit boundaries to enable fast processing by current and next-generation processors. Address fields are 4 times larger than in IPv4. The IPv6 header contains 8 fields. Version: this 4-bit field contains the number 6 instead of the number 4 as in IPv4. Traffic class: this 8-bit field is like the TOS field in IPv4. Flow label: this new field has a length of 20 bits and is used to mark individual traffic flows with unique values, of which routers can use to provide per-flow non-default treatment. Payload length: this field is like the total length field of IPv4, but because the IPv6 base header is a fixed size, this field describes the length of the payload only, not of the entire packet. Next header: the value of this field determines the type of information that follows the basic IPv6 header. Hop limit: this field specifies the maximum number of hops that an IP packet can traverse. Source address: this field of 16 octets or 128 bits identifies the source of the packet. And destination address: this field of 16 octets or 128 bits identifies the destination of the packet. There are multiple methods for transitioning between IPv4 and IPv6, with the preferred intermediate step being the dual stack approach, where nodes have both IPv4 and IPv6 enabled stacks. Old IPv4 only applications continue to work as before. New and modified applications take advantage of both IP layers, usually preferring to use the IPv6 protocol for communication. The dual stack technique is well known and has been applied in the past for other protocol transitions. The dual stack technique enables one-by-one application upgrades to IPv6. However, this approach has several limitations. For example, if some devices are outside of the administrative domain or don't support IPv6, an end-to-end dual stack configuration cannot be implemented. Dual stack requires almost twice as much administrative burden as single stack networks because addressing and routing have to be configured and monitored for each stack separately. In these cases, more advanced IPv6 transitioning techniques such as tunneling or NAT64 have to be implemented. In this lesson, you will be introduced to the services provided by the TCP/IP transport layer and the two protocols running at this layer, TCP and UDP. Residing between the application and internet layers, the transport layer is fundamental to the operation of the TCP/IP layered network architecture. Here we see the functions of the transport layer. The TCP/IP internet layer directs information to the TCP/IP destination, but cannot guarantee that the information will arrive in the correct order, free of errors, or even arrive at all. The two most common transport layer protocols of the TCP/IP protocol suite are Transmission Control Protocol and User Datagram Protocol. Both protocols manage the communication of multiple applications and provide communication services directly to the application process on the host. The basic service that is provided by the transport layer is tracking the individual communications between applications on the source and destination host. This service is called session multiplexing, and the service is performed by both UDP and TCP. The premium service that is provided by the transport layer is assuring reliable delivery, which is performed only by TCP. The primary duty of the transport layer is to track the individual communications between applications on the source and destination hosts. This tracking is provided by both UDP and TCP. To pass data streams to the proper applications, the transport layer must identify the target application. If TCP is used, the transport layer has the further responsibilities of establishing end-to-end operations, segmenting data and managing each piece, reassembling the segments into streams of application data, managing flow control, and applying reliability mechanisms. Reliable and best effort are terms that describe two types of connections between computers. Each type has advantages and disadvantages. Let us compare the two connection types. Reliable is also called connection-oriented. Applications such as databases, web pages, and email require that all of the sent data must arrive at the destination in its original condition in order for the data to be useful. Any missing data could cause a corrupt communication that is either incomplete or unreadable. Therefore, these applications are designed to use a transport layer protocol that implements reliability. Some applications that use TCP are as follows: web browsers, email, and file transfers. TCP is the reliable protocol at the transport layer. To support reliability, a connection is established. Establishing a connection ensures that the application is ready to receive the data. During the initial process of connection establishment, information is exchanged about the capabilities of the receiver and starting parameters are agreed to. These parameters are then used for tracking the data transfer for the duration of the connection. When the sending computer transmits data, the sending computer gives the data a sequence number. The receiver then responds with an acknowledgement number equal to the next expected sequence number. This exchange of sequence and acknowledgement numbers allows the protocol to recognize when data has been lost or duplicated or has arrived out of order. TCP is a complex transport layer protocol. Best effort is also called connectionless. Other applications are more tolerant of the loss of small amounts of data. For example, if one or two segments of a video stream fail to arrive, this application would only create a momentary disruption in the stream. This disruption might appear as distortion in the image, but the disruption might not even be noticeable to the user. Some applications that use UDP are as follows: video streaming and voice IP. UDP, providing best effort delivery, does not need or want to keep information about previously sent data. Therefore, UDP does not need to establish any connection with the receiver and is termed connectionless. There are many situations in which best effort delivery is more desirable than reliable delivery. A connectionless protocol is desirable for applications that require faster communication without verification of receipt. To better understand these concepts, let us compare the basic difference between TCP and UDP using a postal service analogy. An analogy for UDP services is using the postal service to pay your bills. You address each bill payment to a specific company address, stamp the envelope, and include your return address. The postal service guarantees the best effort to deliver each payment. The postal service does not guarantee delivery, and the postal service is not responsible for telling you that delivery was successful or unsuccessful. Like the postal service, UDP is a very simple protocol that provides only the most basic data transfer services. An analogy for TCP services is sending certified mail through the postal service. Imagine that you live in San Francisco and that you have a book that must be sent to your mother in New York. You discover that the postal service will only process letters. You copy the pages in the book and put each page in a separate envelope. To ensure that your mother reassembles the book correctly, you number each envelope. You address the envelopes and send the first one as certified mail. The postal service delivers the envelope by any truck in any route, but because the envelope is certified, the carrier who delivers the envelope must get a signature from your mother and return a certificate of delivery to you. Sending each page separately is tedious, so you send several envelopes together. The postal service again delivers each envelope by any truck in any route. Your mother signs a separate receipt for each envelope in the batch as she receives them. If one envelope is lost in transit, you will not receive a certificate of delivery for that numbered envelope, and you would resend that page. After receiving all the envelopes, your mother puts the pages in the right order to recreate the book. Like certified mail, TCP is a complex protocol that offers precise and traceable data transfer services. The transport layer of the TCP/IP stack contains protocols that provide addressing information so that data can be transmitted over a network. UDP is an expansion of the early TCP/IP suite and is one of those protocols. Here are some of the major functions of UDP. UDP is a simple protocol that provides the basic transport layer functions. UDP operates at the transport layer of the TCP/IP stack. UDP provides applications with access to the network layer without the overhead of reliability mechanisms. Like IP, UDP is a connectionless protocol in which a one-way datagram is sent to a destination without advance notification to the destination device. UDP is capable of performing very limited error checking. The UDP datagram includes an optional checksum value, which the receiving device can use to test the integrity of the data. UDP provides service on a best effort basis and does not guarantee data delivery because packets can be misdirected, duplicated, or lost on the way to the packet destination. UDP does not provide any special features that recover lost or corrupted packets. This functionality does not mean that applications that use UDP are always unreliable. This functionality simply means that these functions are not provided by the transport layer protocol. And UDP has the advantage of providing low overhead data delivery. This advantage is why the UDP header length is always only 64 bits or 8 bytes. Here we see the fields in the UDP segment header. Source port is the number of the calling port, 16 bits. Destination port, number of the called port, 16 bits. Length is the length of the UDP header in UDP data, 16 bits. Checksum, calculated checksum of the header and data fields, 16 bits. And data, the upper layer protocol data, which varies in size. Application layer protocols that use UDP include DNS, SNMP, DHCP, RIP, TFTP, NFS, and online games. TCP is another protocol in the transport layer of the TCP/IP stack that provides addressing information so that data can be transmitted over a network. TCP is a connection-oriented protocol that provides data reliability between hosts. TCP has a number of characteristics that are related to the way in which TCP accomplishes this transmission. TCP is characterized as follows. Like UDP, TCP operates at the transport layer of the TCP/IP stack and provides a service to applications access to the network layer. TCP is a connection-oriented protocol where two network devices set up a connection to exchange data. A TCP connection is a pair of virtual circuits, one in each direction, so that TCP operates in full duplex mode. TCP provides error checking by including a checksum in the datagram to verify that the TCP header information is not corrupt. TCP segments are numbered and sequenced so that the destination can reorder segments and determine if data is missing. Upon receipt of one or more TCP segments, the receiver returns an acknowledgement to the sender to indicate it received the segment. TCP provides recovery services in which the receiver can request transmission of a segment, and TCP provides mechanisms for flow control adjusting the effective rate of data flow between the two services in the session. Reliable data delivery services are critical for applications such as file transfer, database services, transaction processing, and other mission-critical applications in which delivery of every packet must be guaranteed. TCP provides this reliability, but TCP sometimes sacrifices speed. UDP provides speed at the expense of reliability. TCP segments are sent by using IP packets. The TCP header follows the IP header and supplies information specific to the TCP protocol. Flow control, reliability, and other TCP characteristics are achieved by having fields in the TCP segment header, each with a specific function. The fields of the TCP header include the following. Source port, the number of the calling, which is 16 bits, identifies the user application on the transmit side. Destination port, the number of the called port, also 16 bits. This identifies the user application on the receive side. Sequence number and acknowledgement number, tools for reliability mechanisms, each 32 bits, acknowledges the successful receipt of data at the receiver. Acknowledgement number, the next TCP octet that is expected by the receiver. This is 32 bits. Data, the upper layer protocol data, which varies in size and includes the contents of the segment. Header length, the number of 32-bit words in the header. This is 4 bits in size. Reserved, set to 0 and is 3 bits in size. Flags, used in session management and in treatment of segments. This is 9 bits. A single bit that has a specific meaning is often referred to as a flag. Window size, number of octets that the device is willing to accept. This is 16 bits and is the flow control for the data at the receiver. TCP checksum, the calculated checksum of the header and fields that are used for error checking. This is 16 bits. Urgent pointer, indicates the end of the urgent data, 16 bits. And options, the variable length field which contains optional headers that you want to use. The maximum TCP segment size is currently defined. UDP and TCP use internal software ports to support multiple conversations between various network devices. To differentiate the segments and datagrams for each application, TCP and UDP both have header fields that uniquely identify these applications. These unique identifiers are the port numbers. This topic lists various applications along with the application port numbers and short descriptions. The following are a few of the applications that TCP/IP supports. FTP is a reliable connection-oriented service that uses TCP to transfer files between systems that support FTP. FTP supports bidirectional binary and ASCII file transfers. Telnet is a predecessor to SSH and sends messages in unencrypted clear text. Most organizations now use SSH for remote communications. HTTP and HTTPS define how messages are formatted and transmitted and what actions browsers and web servers take in response to various commands. HTTP and HTTPS use TCP. DNS is used to resolve Internet names to IP addresses. DNS uses a distributed set of servers to resolve names that are associated with numbered addresses. The following are just some of the applications with the application port numbers. Go to the Service Name and Transport Protocol Port Number Registry website as shown on the screen for a complete list. The following key points were discussed in this training. WANs provide connectivity between geographically diverse sites using a variety of connection sites. An IP packet is a self-contained, independent entity that contains data and sufficient information to be routed from the source to the destination. Unique 32-bit logical IP addresses are used to identify the location of specific devices on an IP network, and those addresses are divided into 5 categories that are called classes. For scalability, IP networks are divided into subnets, and subnet masks are used to interpret the IP address and identify the network ID, subnet ID, and unique host ID respectively. Due to IPv4 address exhaustion as well as other industry needs, IPv6 has been developed to include larger 128-bit address space, strict aggregation, and auto configuration. There are 2 protocols, UDP and TCP, used at the transport layer of the TCP/IP protocol stack. Both protocols provide tracking of communications between applications on different hosts. And UDP is a best effort connectionless protocol used for applications that require faster communication. TCP is a reliable connection-oriented protocol that provides sequencing, acknowledgments, and flow control.